when we had people register for this webinar, we asked a simple question at the end of the registration: describe the challenges you are facing with your existing part design. We took a sampling of this data about a week or two ago just to get an idea of the direction we wanted to take this webinar. What we were finding is overwhelmingly folks who are registering were interested in issues with supports. And so things that we're calling support free, but anything having to do with the service finish of the supports, actually building the supports, having problems post-processing. Lucky for us, we have the industry's expert at doing this today. So our speaker will be Brian Spink. He's our applications engineering manager at VELO. He's the world-renowned expert at consulting customers and bringing their parts and printing them on VELO3D Sapphires. Virtually no one in the world more qualified than Brian at doing that. So he's the right person to be talking with us today. He joined VELO in 2015, and he's done a bunch of different roles, like a lot of the people here have, a lot of different hats. He's currently managing the group for applications engineering, and he has a BS in physics from Bloomsburg University. So Brian, I'll turn it over to you.
Thanks, Mike, and thanks for everyone for joining today. I think kind of overarching goals for me today is to kind of get rid of some of the ambiguity of exactly what the angle rules are and what your dimensional limits are. So I hope that you can come out of here with a better understanding of what VELO's capabilities really are, and that you can start to look at the parts that you've been looking at a little bit differently, and hopefully shedding some light onto where VELO3D can potentially add value to manufacturing these parts. So bear with me for a couple slides. I'm going to do a bit of 101 on where the root of what we're talking about is coming from, and kind of why do you need supports. And so very high level and super simple looking at it. These couple graphics here. The basic laser melting process, what's going on is you have a solid substrate of metal sitting in some sort of powder bed with some sort of constraints, and you run a laser and melt this powder back into the substrate underneath it. What happens when you melt this metal is you have subsequent cooling, and the metal that has solidified and cooled shrinks and contracts. And sort of the battle between this contracting newly melted metal and the existing substrate underneath it caused this tension, this residual stress. And in kind of the simplest example I'm showing here, you have this bit of potato chip effect on the metal itself as it contracts. Obviously, when you melt parts that's much more complicated than this, you kind of have, I'd say, a couple general scenarios where you have this same effect accumulating throughout a large volume, and that'll result in levels of residual stress throughout the entire volume of the part, and kind of global gross distortions across the part. You also have this happening very locally. And so on things like sensitive skins, on low angle down-facing surfaces, this can be pretty catastrophic. So looking at a couple examples, if you're familiar with Metal AM and you've done some work in it, I think you're familiar with some of these, with some of these issues. So I'll be using the term breakdown mostly for this, and when I talk about breakdowns, I'm talking mainly about defects that occur on the surface. So if we look at the example on the left, we're looking at a conical shape, a very shallow angle conical shape, and we're looking at the down-facing surface of this cone with some supports in the center. And what we see on the right cone is all these defects. And what's happening, or the reason why these defects are forming, is the process and the melt pool are becoming unstable. This could be a combination of the process that you're feeding forward, maybe what's happened on earlier layers, maybe it's combination with warp, but you have a melt pool that becomes unstable and drills through the metal substrate below it and out onto powder and accumulates these large defects that obviously have a negative effect on the surface finish. Another general case and breakdown that I think a lot of us are familiar with is high levels of warp. Right, so you're seeing, again, a conical shape, and if you look at the edge of these examples here, there are breakdowns, and there's obviously surface breakdowns too, but you can see that the shape deviates from nominal, especially towards the sensitive skin, like I said. So the residual stress battle is being kind of lost, so to speak, on the leading growth edge of these parts, and on the sort of the left tip of these parts as they're grown, leading to significant warp. This can lead to deformations, it can lead to surface defects, it can lead to negative interactions with your recoder mechanism. And so in general, the way people will address this is to just add support material. The support material does a couple things. It mechanically restrains or anchors the part down to keep it from warping up. It also acts as an energy sink when you do have the cases where the melt pool becomes unstable and it might punch through the substrate or spill over the edge of the substrate. If there's support material there to absorb that energy, things don't go out of control so much. Obviously, what we're mostly talking about here today is the drawbacks of these supports and why we don't want to have to include these in our prints. So there is another option to supporting, and it's basically to control your process and to allow for some unique processes to run. And that's what VELO3D has done, and what I'll get into a little bit of the details of. And we've done it through proprietary hardware and a lot of advanced process control. So high level of process control, you can think of a lot of other metal AM systems have really only a small handful of different types of processes that are applied over every kind of unique geometry that you try to throw through the workflow. What VELO does, and a lot of work in the preprint software does, is it recognizes many more unique geometries, especially using angle-based rules and thickness rules to apply unique processes feed forward to these geometries to control and have a more tailored process to this, so your process doesn't lose control and you don't break down. Another added level of control that VELO has introduced is a closed loop control for certain process parameters. So we have a couple of sensors that monitor the melt pool in real time. And using this data, we create a closed loop that can adjust some parameters, some laser parameters in real time to help control the consistency of the melt pool and avoid these breakdowns. So kind of a quick overview before we get into the numbers of the process. I want to kind of create some framework. If you're not familiar with the VELO Sapphire system, it's a two 1 kilowatt laser system. The lasers have full field capability. They have full overlap capability anywhere on the build platform. They have in situ correction for overlaps or overlays, so you don't have to worry about things drifting during the build. The build volume, we have a circular build plate in our machine. It's 315 millimeters round, 400 millimeters tall. The two fully released processes that we have right now for Inconel 718 and Ti64, they use typical powders, 1545 particle size distribution. We're using argon to inert. The recoder mechanism is one of the key pieces of hardware here, and its specific action is a bit proprietary, but to kind of tell you what the net result of it is we call it a non-contact recoder, and what it means is there is no interference between the parts being built in the powder bed and the recoat mechanism itself. And so you essentially have a gap between those two components, and you don't have any interference, and we'll get into what this leads to here pretty shortly. Also, the capabilities that I'm talking about today are for a 50 micron layer process. We've explored many others, and looking forward in the future, we're going to have some processes that adapt specifically to layer height to help enable some other things. But today, the capability I'm talking about is for these release processes, and they're in a 50 micron layer configuration. Here's a quick shot at kind of the build chamber, the top view of the build chamber. Again, round build plate. We have two lasers. The normal indices are listed there with the two small red circles. The recoder moves front to back and parks itself in the back, comes in and out every single layer. The gas flow goes left to right. We have laminar flow across the build plate at a high rate, and also some advanced flow characteristics in the chamber to allow us to use full 1,000 watt throughput for our bulk fill processes if need be, without any degradation of the process. Now you got the overview of kind of how the machine's laid out. Another couple just really high level specs to cover. We have 99.9% density, so some of the enablement you're going to see here is not coming at the expense of density. And the general dimensional accuracy spec we have is 50 microns, plus or minus 0.2% of the dimension that you're trying to evaluate. We have available, you can reach out here. We have available formal material data sheets on both Ti64 and Inconel 718. If you want to see a little bit more detail on, especially mechanical properties, is something we're not going to touch here on today, but we have good analysis of on these data sheets. So let's get into some numbers and let's get into some rules. So I'll go through a few examples of dimensional limits. First thing I'll touch on here is thin features. So we're looking at thin pins and thin walls. Kind of break those up because they behave slightly different. The first spec for each one is the minimum thickness you can achieve. In both cases, this occurs in a vertical orientation. And to kind of give you reference for how I'll speak about angles moving forward, 90 degrees is what I'll call vertical. 0 degrees is down facing horizontal, and 180 degrees is up facing horizontal. So you can see on these plots, I've mapped out the dependency of the minimum achievable thickness for each of these features as a function of angle. And so you can see as you reach down an angle so it approaches horizontal, the minimum thickness you can achieve does vary a bit. And so I want to make sure that, this is a theme I'm kind of carrying on here, is to not have such a binary or single number rule, because things don't work exactly that way. So you can see that it is a roughly linear relationship. As you go down an angle, your minimum thickness achieved is a bit higher. A couple important notes is the aspect ratio of these features is only limited by the height of the build, right? So you can take a 130 micron vertical pin and you can build it the full 400 millimeters tall of the build height. This gives you something like a 3,000 to 1 aspect ratio. So the only limit is how tall the build chamber is. It's the same with walls. The other mention for the walls is there's no directional dependence for the walls relative to the recoder. This goes back to the proprietary recoat mechanism I mentioned before. There's no interference between these thin features and the recoder itself. So it's not shoving it out of the way. It doesn't matter how you've oriented the wall relative to the direction of travel of the recoder. So I'll give a couple examples here. Top right, we're looking at an array of small pins of varying sizes, thicknesses, the diameters, and varying heights. And you can see roughly from the picture that consistency is maintained regardless of the height of the print. They'll give you some scale here. This block is about 1.5 inches wide. But as I mentioned, if we felt so inclined, we could print these pins as tall as the full build height. For thin walls, we're showing a kind of a mock-up heat exchanger type geometry. This is about 6 inches in diameter for a little bit of scale. You see what we've done here is we purposely, for demonstration purposes, oriented the thin walls radially in every direction to show consistency in the quality and the thickness, irrespective of the recoder direction. Okay, moving on to holes or tilted tubes. Our maximum ID that we can achieve without supporting the ID of a horizontal tube is 40 millimeters. The minimum ID of a small hole that we can achieve is about 500 microns. This is currently being pushed down. I list this spec because we can do this confidently and we can do it with high fidelity. The types of geometries you run into are a lot of manifolds. I have this turbo volute example here on the right. We'll get into this in a bit more detail. It actually has a lot of features that we can use for demonstration. This one is a bit straightforward. What I wanted to pair with it is the tilted holes. And so the behavior changes quite a bit if you tilt tubular geometry like this. And so the maximum ID grows greatly if you tilt this thing at about 10 degrees or more. And I'll get into the details of exactly why that is and how these growth directions, or the shape of the propagating leading edge matters, and why you can print the ID without adding supports, but the OD is a bit of a different story. Also, kind of working off of this, I have closures here in general. Domed closures, we can do a maximum ID of about 100 millimeters. I'll get into some examples again with this turbo volute a little bit later where you see this. This is kind of any internal cavities, a lot of manifold type geometries where it doesn't have to be a perfect circular spherical geometry, but these types of closures VELO can print without adding support. And when you have internal geometries, really looking at this turbo volute and how the closure is working its way up, it can be extremely hard or impossible to be able to reach in and remove supports. So in some of these cases, you're taking something that couldn't be done with any other AM process and enabling it on a VELO system. And here for reference too, I also have a maximum horizontal or 0 degree span of 10 millimeters and the minimum about 200 microns. And you're seeing a part here on the right where the largest span on the left is about 10 millimeters. And the one in the image, the minimum span there is about 1 millimeter. It's not quite down to 200, but we can maintain 200 microns between two vertical walls consistently without any closures or defects. All right, I'll touch on surface finish. This again is something that I don't like to give like a single number for exactly because it depends much on the minimum thickness specs that I gave. It depends on the angle that you're printing at, or the angle that your surface is at. The sample, the geometry that we use often is this kind of CAD you're seeing right here. These are roughly 10 millimeter square blocks that are tilted at different angles. And it goes from what we'll call 90 degrees or vertical on the far left all the way down to a 10 degree down facing surface on the right. So to get into the numbers of this, you can look at the plot. And so your surface finish is certainly a function of angle. And you can see that you form this roughly U-shaped curve when you plot angle versus roughness. The roughness measure I'm using here is SA. SA is just the area analog of RA, which is more common. SA, we like to use it because it's a more dense data set. It gives a bit better generalization of the characteristics of the morphology of the surface. But in general, SA measures extremely similar to RA or even a little bit higher sometimes. So a few notes to take away from what you're seeing on this plot are that the minimum roughness is achieved near vertical and even slightly top facing a vertical. And the maximum roughness we get here is just under 14 microns SA. And the minimum being between 3 and 4 micron SA. This is pretty typical. What you're seeing in the bottom image is that gauge block that I showed in CAD, but kind of tilted and rocked back. So you're looking at all the down-facing surfaces. And you can see there is some roughness change. There's a little bit of morphology change, but you can see for the most part, it's quite stable. On the 10 degree, all the way out on the edge, you may start to see a little bit of curl on the edges. And I'm going to get into those types of rules to follow, but you can sort of get an idea here of what the surface morphology looks like and the consistency of the surface for this angle range. So let's get into the angle guidelines. As I said, it's not a 45-degree rule. It's not a 10-degree rule. It's not one single number. It's obviously dependent on quite a few different factors. Being able to print the feature without supports is certainly highly dependent on the angle normal to the surface that you're doing, but it's also dependent on some other things. It's depending on the curvature of the leading edge of growth of the part, and I'll get into those details kind of moving forward. The number of layers that you're trying to propagate this specific feature, the angle of incidence of the laser relative to the angle of growth that you're doing, and other local geometric effects that affect how the energy is being absorbed into the part locally and how the melt pool is behaving locally. What I'm going to use here for the next few slides to kind of describe basically whether you need supports or not is, again, what I'm calling a probability of breakdown plot. And this is a contour plot showing your probability of breakdown being high, moderate, or low. Low meaning you're pretty safe that regardless, you're not going to have to worry about any sorts of breakdowns. Yellow is getting marginal, and so there's a good chance that you need to consider changing things. You might add supports, you might change the geometry, you might change the orientation. And red, you're almost guaranteed to be running into some problems, some sort of build failure associated with these types of breakdowns. So I'm plotting everything out as a function of angle on the x-axis and height being z height that you're propagating this particular feature for. And we'll have a cut line to kind of indicate that once you hit a certain height, it really extends up all the way through the full build height. Okay, so let's get into a couple examples. Every geometry you have is unique, right? So you can't generalize this exact rule, this exact plot for an infinite amount of parts, obviously. But what I want to try to do here is bookend the issue, give you a couple of proxies that you're familiar with and a handful of rules that you're familiar with on simple geometries, and let you infer in between and kind of interpolate some of these rules on real geometries that you're experiencing. The first and probably the most simple is just taking an angled plane, right? I want to break this into two examples, the unconstrained and constrained plane, and how they behave differently. Looking at the unconstrained plane, it's certainly a less favorable, less stable geometry than the constrained plane, because what you're going to have here is the behavior of the process is going to be less stable at the corners because of how the energy is being absorbed there relative to the middle of the plane. And so the constrained plane is going to act a bit more stable. And as the constraint or the walls come in on the plane, this becomes more and more stable, and you can go down to lower angles, or you can propagate it longer. And as the walls spread farther and farther apart, it somewhat converges to being the unconstrained plane example. So if we put this on contour plots, this is roughly what it looks like. You're seeing that in the unconstrained plane, that marginal band is coming out quite a bit more. And so for a given, so we'll call it a low angle, you're looking at the 10 to 15 degree range. If you're printing, say, in the 5 to 10 millimeter range, you can see that you're going to start getting into some risky geometries. And you can infer other rules and kind of how this would actually be shifted for your specific part based on some of the other rules that we're talking about. But you can see the relative relationship here. If you constrain the edges of this planar geometry, that this becomes safer, and the moderate band sort of subsides farther, and you can print a bit longer or print a lower angle, whichever way you'd like to look at it. Next example that I like to use a lot, and this is a really important relationship that I try to drill into anybody that I'm teaching, not just for VELO, but AM in general, is the curvature of the leading edge of the part. And so what I use as the most simple proxy are cones. And I use an inward growing or an outward growing cone, as you see on the top here, and an inward growing cone on the bottom. And what's happening in this part on a high level on this type of geometry is you have two basic forces that are working together to that may lead to breakdowns. One is sort of global residual stress in the bulk of this part that's shrinking each layer, kind of like the very simple example I showed in the beginning, and pulling the geometry inward towards the center of the local mass. And the other one is the skin process, the melt pool of the skin process, which basically forms a ring around this geometry. And when it melts, it does something similar, but it's in a different orientation. It contracts and wants to pull inward. If you look at the example of the outward growing cone, both the bulk and the ring on the outside are contracting inwards towards the center of the mass there. They're working together to both warp the edge up. And so this geometry, this outward growing, or I'll call convex moving forward geometry, is less stable than if we took the other example, being because you have a ring on the center here that is shrinking and contracting and pulling inward, and you have across one of these cross sections on either side of the part, you have bulk that's shrinking in towards the center of mass, towards my pointer here. Those two are working against each other, kind of combating each other, and they actually create one of the most stable geometries in Metal AM. And so when you look at these two contour plots next to each other, they behave very differently. You can see that the red and the yellow, the high risk of probability and the moderate, encroach much farther out into the angle ranges. And so this is where it comes to, like, you can print angle X, but it depends. And this is how kind of different some of the examples can be. And so if you look at the concave inward growing example, this geometry at a relatively very low angle, 10 degrees, which is what we sometimes quote as our minimum allowable angle to print, is very stable all the way throughout this. And so you could, in theory, print an inward growing conical geometry as large as you could fit in the build volume. However, if you look at an outward growing cone, that story changes quite a bit. And in some cases, you can get to about the 20 to 25 degree range, and if it's in the right orientation, it propagates high and far enough throughout a build volume, you start to get risky. And the 10 degrees certainly puts itself at a very high risk if you don't support it to having breakdowns. So putting this to some real examples, first I'll have this shrouded impeller example. You can see the total geometry, kind of a couple views of it up in the top right. And what I want to focus on here is the most critical feature of this type of geometry, which is the internal flow path. So please excuse the outer surfaces here from the equation. I don't want to focus on this flow path for the sake of our example and relating this back to some rules. If you have it oriented like this, your internal flow paths have basically a relatively easy, safe up-facing surface and a relatively difficult or dangerous down-facing surface. Dangerous meaning if you don't support it, you have risk of breakdowns. And if you look at this down-facing surface, it propagates from about 30 degrees here in the beginning, and then to give you some size, say this is about 10 millimeters in Z height span, it goes down to about 10 degrees at the end. And so what you've got is this dynamically changing conical, outward conical growing shape, or this convex shape. You have the dynamics of some real parts where you can look at the constraints that the veins pose, and you can also start to infer some things about the planar geometries. But just to focus on this sort of global behavior of this conical shape, if you look back, or if you think back to the slide before, when we had the contour plot of the outward growing cone, you think about, okay, I'm in the angle range here of about 30 to 10 degrees. If I come over here and I think about, all right, if I've got to propagate this thing 10 millimeters or more, I am, for a cone, getting myself up into some obviously risky areas here. There are some other constraints and dynamics here. And like I said, I'll reiterate, with all parts, there's always more than one thing going on usually. And you're not printing a simple cone most of the time. But if you look at the global behavior of this, you can see that the conical shape is going to behave pretty unfavorably and put you at pretty high risk if you want to avoid putting supports in this critical flow path. Conversely, if we flip this thing over, again, only focusing on this critical flow path, now the relatively high risk down-facing surface keeps the same angle range. So you're looking at about 10 degrees down here and about 30 degrees up here. but the general global shape is now an inward growing cone. And looking back at the contour plot I just shared, obviously this is quite a bit different. So if you're looking in the 10 to 30 degree range, you can propagate this about as far as you want, as large as you want, and maintain stability, avoid breakdowns in the process. And if you factor in the fact that we talked about constraining a span actually adds stability to it, it only helps your case here. So in this orientation, we can just about guarantee that for this angle range and this level of propagation that we're going to be safe, and we don't have to add supports in here, and we're going to avoid breakdowns. Moving to a bit more of a complicated example, I'll try to kind of give some other examples of some of the same things and some other things to look out for. So top right, I want to show this turbo volute again that I had mentioned before in this rough orientation, and the tilt you're looking at relative to the build place on the order of, say, 30 degrees or so. There's a lot of unique features that come up in this part, but we can apply our kind of high-level general rules of thought to how we would approach supporting and orienting this part. One area I want to focus on right away is you have this closure here, right? So this comes up, this tube that's wrapping around the back of the volute housing is going to close up. There's a couple rules you can think about here. The leading edge of this shape is slightly convex, so it puts it at a little bit higher risk than if it was concave, although it's not very severe. The curvature, the radius of curvature is still quite large. What this probably behaves more like is you can refer back to your horizontal tube rule. And so you can think about your 40 millimeter rule. And if this tube is under 40 millimeters and you don't have any other very blatant examples of unstable geometry, then you can basically peg the ability of your ability to have this closure without supports on roughly that 40 millimeter rule. As this closes, this immediately turns into a very different geometry, and it turns into this concave geometry. And when you're thinking about just this geometry, you can think about the tilted tube rule then, right? It's starting to form this nice stable concave shape. And remember, the rule there is 100 millimeters thereabouts at 10 degrees or higher tilted angle. And so the lowest angle is right here, and it actually nestles itself, although it's not a complete closed tube, the lowest angle feature here of this curve is well within a nice stable concave shape. And so it behaves similarly to an inward growing cone locally. You could think about that here. Another feature that I want to look at here is the inner hub here. The inner hub is a flat surface. You can kind of see in the picture up here, ignoring sort of the holes for the sake of this argument for a second. For a lot of the beginning of the build, the first half or so, say, of this hub being built, this is basically a plane constrained on one side. And since, say, we've tilted this at about 30 degrees or so thereabouts, remember from those planar rules, it's well within the safe band, constrained or unconstrained. And so it's a pretty stable geometry. Something to look out for, though, commonly is as these two planar geometries kind of come together and form this point, the surface of the bottom of the hub still remains at about 30 degrees. And if that's at 30 degrees, then this inner cylindrical surface, if it's perpendicular to it, is about 60 degrees. And so both of those planes, obeying rules on their own, are quite safe. But something to look out for all the time that I see get missed quite often is this edge or this spine actually quickly towards this closure approaches very low angles and propagates for a significant amount of layers. On top of that, it also forms what you can kind of think of as a very extreme case of convex geometry, where your curvature, which isn't, it comes to a point, but your curvature is kind of extreme here, you can think, and it isolates this thing from mass below it, and creates a very different behavior than something that has a lot of mass below it. So what you're going to do is eventually, even with the closed loop control that we have to help mitigate some of these variabilities, you're still going to run into some issues with geometry. Extreme geometries like this, you're going to have too much energy put in it. It's going to lose stability. And so the net here is that you have to add some supports to this type of geometry. Flip this geometry in a different direction, and you're starting to see some different things. You see some similar features. So you have some of the tubular features behave pretty similarly. The planar features behave pretty similarly. However, now in this geometry, what you've got is a closure. You remember a dome closure example where the rule there was maximum of about 100 millimeters in diameter. This, again, as most real part examples are, they're not perfect direct relationships to the proxy that I gave, but you can think about it in a similar way. Or if you tried to estimate the radius of closure around here, took an average, and if you think that it falls within, say, about that 100 millimeter rule, then you can be confident that you can close this feature without having to add supports. If it's large enough and you can infer that the radius is too large, then you'll probably have to add supports. This, again, is a different example of the pointed closure. It happens in an open face tube. This, again, so when you're looking at these parts, of course, a lot of what you're doing when you're setting up the parts to manufacture additively is you're taking all of these risks and you're comparing them to the relative importance of the surface, importance of not having to support it. So you think about what your post-processing needs are, you think about what your performance needs are, you kind of prioritize the most critical surfaces to not support or to have optimal quality, and then you change the orientation and balance out and shift where you're going to have to add support, so you have these types of features to different areas of the part. And so that's what I kind of started to show, that sort of game you play back and forth with these two basic examples of orientation. One last thing I want to touch on, because I know that we've talked about this publicly before, is the ability to print floating parts. Floating parts means it's not attached to the build plate at all. There are no added support material. There's nothing linking it to the plate. It starts in powder, and the main enabler here, besides the process control, especially near the start of the geometry, is the unique recoder mechanism. Because there's no interference between the part, which is now floating and very loose in the powder, and the recoder mechanism itself, you can propagate a part floating in powder, and it's pretty rewarding to be able to open a build chamber and just reach in and pull a part out, and that's it. You don't have to change build plates. You don't have to remove any extra support material that's attaching it to anything. There are a couple basic rules here, though, that limit this feature quite a bit. And so few rules are: it must originate from a pointed geometry. So again, you can't print a large flat plane because there will still be residual stress. Even with our unique processes, there will still be bulk residual stress that will cause something very broad and flat to warp up if it's at a very low angle. So if you can start it from a point, you can potentially print this part. The second main rule is it can only start from one powder start. So if you look at this simple V-shaped geometry at the top, if I have it oriented like this and I have two powder starts here, they'll both each individually start out without a problem. They'll propagate all the way up until you have this connection point. When you have this connection point, you're going to build residual stress between the two bodies that you're joining. And that residual stress, because there's no constraint to the build plate or anything, will actually kick these two parts around and you'll have massive distortion, and you may lead to a build failure. Now, if I flip this part upside down, I'm obeying the single powder start rule. I originate from one point, and there's no kind of combating bodies to fight for with residual stress. And so you'd be able to print this thing without issue if it was oriented like this. Kind of looking at a real part example, a lot of what I see where this can apply is two things. One, you already have a corner on a part, and if you rock it back on that corner, you won't have another powder start. That's the case of this mock-up turbine blade. The other example is you have something that's nearly a point, and what you can do is you can add what is kind of referred to as a floating support. So if you took, like, you had a slight flat here picture, and you couldn't start the flat, but the rest of the part obeyed the rules to the left. If you added just a little cone to the bottom of it, we'll call it a floating support material, then you could propagate it. And in some cases, when you balance out the post-processing that you'll do, the slight bit of added height from that floating support, the business case can still be really strong. Factor in all of the other things as far as build changeovers and not having to resurface a build plate. And the way that one really powerful factor about this is you can stack parts on top of each other or next to each other, nested and overlapped in Z height. And where the business cases really get strong here is where you can, compared to attaching to the build plate, you can increase your average cross-sectional area per layer. And in general, when you do that in Metal AM, it increases the efficiency of your build and makes for a better business case. Again, I want to reiterate, I gave a few general simple rules, and what I wanted to do is bookend this. I want to give you guys ideas to be able to interpolate in between. We haven't solved here in this presentation every unique geometry that everybody's encountered, of course, but I hope that it kind of gives you a bit of a frame and doesn't just say, hey, we can print to 10 degrees and leave you to your own devices. Kind of gives you some extreme cases for you to infer about your part. Thanks, everyone.